like picking problems from the homework, but exact equations are what section? 2.4. So hopefully we can do these problems. Let's see. Number 5. Just going for it, aren't you? All right, we have to see if it's exact. And if it's an exact differential equation, then we can solve for it using the technique that we haven't really seen yet. So let's see how to solve for a differential equation that's exact. We don't know if this is exact yet, so we have to check if it's exact. And remember, we call it M and N. I forgot. Did I encourage you to do that, or did I say that's just more confusing? I think. All right. So I think let's go for it. Let's assume this is M. And this is N. So the M is the one with the X. And to check if it's exact, what we need to do is we need to take the derivative of M with respect to the other variable, right? With respect to the other variable that it's the differential of. So take the derivative of M dm, and this is partial derivatives. And all that means, we're not going to look into the theory of that, that's Calc 3, but all that means is you're going to hold the other variable constant. So we take the derivative with respect to y, the opposite of that variable. And with respect to y, start off with a product rule. Derivative of the first times the second, plus the first times the derivative of the second. And then with respect to y over here, treating x as if it was a constant, that's e to the negative xy times the derivative of the numerator, which is negative. Y is the variable, x is a constant, so what should this be? Negative x. Okay. And I don't usually care about simplifying it, but for the sake of being able to check if this is equal to something else, I would probably want to go ahead and simplify. So this is ln y plus 1, and negative is a positive, x e to the negative xy. All right, so that's one of them. And now I want to take n and take the derivative of that with respect to the other variable from the differential, so with respect to x. So if I take the derivative of this with respect to x, the derivative of 1 over y with respect to x is 0, because that's a constant. And now I have to do a product rule here. So the derivative of the first times the second. Well, I don't need a product rule here. It's just ln y, right? Yeah. Period. It's not exact. All right, we didn't get to do it. We'll do another one. All right, so in this case, it's not an exact differential equation. So there is possibly a way to solve for this by multiplying by some special integrating factor, but we're not going to do that. Maybe I'll provide a video where I give you an example where if something's not exact, we'll multiply it. We'll find an integrating factor and multiply it by that so that it would become exact. But we're not going to spend too much time on that. So let's move on. I guess we should check, huh? No, it's not. All right, let's do the one before it. Looked like it was hard. No, I'll do the one before that. Could this possibly be exact? All right, maybe number 4 is exact. Let's take a look at number 4. So determine whether this is exact, and if it is, solve for it. So let's do the same thing, m and n. Oh, be careful there, this is an equal sign. So remember, exact equations, we want it to be set equal to 0, so let me just change this into a minus and set this equal to 0. So that essentially I've brought the left-hand side, the right-hand side over to the left-hand side. So check to see if it's exact. We'll take m and take the derivative of that with respect to y. It's 0. That's a minus 7y. Sine x is constant, so 2y sine x. All right? I hope the second one is the same after I take the derivative of n with respect to x. Let's see, with respect to x, that's 7y. What? Oh, yeah, there was a 6 here. It disappeared. So the negative sign, we'll make sure that we're going to distribute that later on, or as we're doing it, that negative sign gets distributed. So the first term is 7y to the 6, and now we have one more term with respect to x. 2y is constant. And cosine, derivative of cosine is negative sign, so that makes this positive, which matches up. All right, great. So now we have an exact differential equation, and now this is where I was trying to explain last time. We're going to backtrack, and this is a derivative of some sort. Okay, so according to the first page here, we assumed from the beginning that this came from, let's call this a little background here. This came from a function of 2 variables equaling to a constant, and then I took the differential of both sides, and the differential here is the partial of f with respect to x dx plus partial of f with respect to y dy equal to the derivative of a constant of 0. So we're assuming, because this is an exact equation, we're assuming that this originally came from a function, f, that's a function of both x and y. And what that means is that according to your differential equation, your exact differential equation, we can essentially identify the derivative of f with respect to x as the term m that we saw earlier. And we can identify the df dy as a term n. So remember, we're trying to obtain f, the original function f, and then be able to solve for y there. Yeah?
Is it always going to be in that format? Like this plus just because of the rules?
This plus? Yes, it's always going to be in this format. So when your differential equation has this, you're going to make sure you want to carry that negative sign. Okay? Don't lose a negative sign. Bad things can happen. All right. That means m is equal to the partial of f with respect to x. So if we write it like this, partial of f with respect to x is equal to m. And remember, we want to obtain the original function f. So if I had taken the original function f and took the derivative of that with respect to x, that's how I got m. If I want the original function, I want to go backwards. So I want to take the integral of this with respect to x. And by doing that, I would obtain my original function f. So let's do that. So I'm hoping for f here. So I'm going to boldly call it f and hope that it's going to be okay. It's a function of x and y. Now I want to essentially then take the integral of m. Where's m? Not this one, not the check part, but the original m. X minus y to the 7th plus y squared sine x. I want to take that whole term and integrate it with respect to x. So just like we took the derivative, partial derivative with respect to x by holding y constant, when we integrate with respect to x, we're also going to hold y constant. So the antiderivative of x with respect to x squared over 2. The antiderivative of a constant, y to the 7th is a constant with respect to x. The antiderivative of y to the 7th with respect to x is what? X times y to the 7th. And this has a negative sign. Constants. So y squared is a constant with respect to x. The antiderivative of sine x. Negative cosine, right? Just get rid of that plus. And y squared is constant. Move that outside of the integral or whatever you want to do. And then the sine is going to become cosine. Okay? Now remember when we take antiderivatives, there's a plus c. Right? Let's think about this for a minute. We took the antiderivative with respect to x. If your original function f, if you took the derivative of your original function f with respect to x, I know that if I had a constant like 3 or 5 or pi or e, that would disappear. What else would disappear? If you had a term with a y in there, that would also disappear. So I want to put a plus c here, but I can't just assume that the c's are just constants. I have to allow the possibility that there was a y function. So I'm going to append this with a g, let's just call it c, c1 as a function of y only. If there was an x in there, then that would have been part of the integral that we would have seen. That the term wouldn't have disappeared. But if you had a pure y term in there, like an ln y or an arc sine of y or something with a y in your original f, and you took the derivative of that, that would have disappeared. So we want to make sure that we would account for any of those and possibly recover it somehow. Okay? Is that cool? All right. This is one possible answer. And what we want to do is, since we took two derivatives, we should probably expect to do two integrals. And we know that the derivative of f with respect to y was equal to n. And so in recovering our original function f, we would probably want to take the integral of this with respect to y. And here we would get another view of our original function f. And hopefully it'll match up, except maybe the constant with respect to y. So what is our m or our n function? This is a negative, so keep that negative there. 7xy to the 6 plus 2y cosine x, and do this with respect to y. All right, the first one with respect to y is what? So 7x is constant, y to the 7th over 7. Well, that would cancel the 7. And this also has a negative, right? All right. 7's cancel. We got a negative. Now the next one with respect to y, so cosine is constant. So what's the antiderivative of y squared? Or that's the antiderivative of 2y. Y squared. So that's y squared cosine x. Now, in the same token, we took the derivative of f with respect to y to get n. Yeah, because this gets distributed, right? Negative signs. Okay, so likewise, and I'm going to call this C2 subscript. That's the name of the function, and this is a function of x. So some people do this differently. I think some people, they take the integral of 1 and then take the derivative, and then they come up with their answer or something like that. I actually prefer to do it this way because it's a matter of comparing. And at this point now, what you want to do is you look for the terms that you have in common. So I know that f of x has at least this term, negative x y to the 7th. I know that it has this term, minus y squared cosine x. Now, this term was missing, but I know that there's a constant with respect to x that was missing here. And so this must be that, quote, constant. So this must be part of my f function. And then if I look at the bottom here, I don't see any terms that have a y by itself, just a y. So I think I must be all clear there. Okay. So if I take this and then make this equal to a constant, so this is what we had. This is our differential equation. We were working backwards to try to get our original equation back. So we identified the function, a function of x and y, and that must have been equal to a constant. So equal to c. So this is your differential equation. Now, if for some miracle we were able to solve for y, then that's a big plus for us because we can get our function as an explicit function of y. But solving for y, this is y to the 7th and y squared. You can't solve for that. So we have to just settle for this. This is your implicit solution. Which means it's an equation with a y in it. If I graph this in a graphing program, I would see my curves. So that must be the solution. Okay? All right, we finished the problem. I guess we should check if it's correct, right? if it's exact, solve for it. And so we solve for it. You get a negative x times 7 minus y squared cosine x plus 1/2 x squared equal to a constant. Right? Looks good. All right? So that's how you solve for exact equations. Any questions? You want to see the solution? Nah. I have a graphing program that's easy to use, so I usually like to see it here. Minus x times y to the 7th minus y squared cosine x plus 1/2 x squared equal to, let's see, set it equal to 0 and see how it looks like. Ooh, cool. Equal to 1. 2. Wow. That's cool. Negative, maybe? All right. So we can lay this out and have a whole bunch of equations. So we can see the family of solutions. I didn't look at how to do. I think I vaguely know how to do a slope field on this, but I'm not going to try right now. But if you looked at the slope field and see how the curves go, they would follow along the slope field. All right, that was nice. Any questions? So that's going to be your example for dealing with exact equations. And we're going to move on to the next section. The next section is on substitution. Is that okay? We'll move on. So your integrals, back in Calc 2, when you first learn your integrals and you start learning all these techniques, you're basically stuck with 9 basic integrals, right? You have these 9 basic integrals, and what you need to do to integrate something is to make your integral look like one of those. And so if you had an integral that looked like x e to the x squared dx, if you look at the table, that's not in one of those tables. But if you're clever enough to do something to make it look like one of those things in your table, then you can integrate it. So that's a story here with the substitution, is that you have some random differential equation. Can I make some clever substitution on this differential equation to make it look like a separable differential equation, a first order differential equation, or something? Okay, so that's the idea. You can solve for this, by the way, right? Use substitution, and you're done. X squared, yeah. But there's an x out here that makes it a U substitution problem. All right, there's 3 main types of substitution that we're going to discuss. And the first one is identifying a type of function called a homogeneous function. And it is unfortunate that the term homogeneous means something else later on in the semester. It actually means something else in linear algebra also that is similar to what it's going to mean later on in the semester in this class. I just confused myself there. usually when you hear the word homogeneous equations, it's something is set equal to 0. But this is not one of those cases. So the term homogeneous function in this case is a function of x and y, where if you replace it with something with a t in it, or not, you replace the x with t times x, you replace the y with t times y, your function will look exactly like your original function after you've factored out. It's like checking for whether a function is odd or even, where you're able to factor out a negative sign. Here, it's the same thing. Are you able to factor out a t to some power? So that's the definition of a homogeneous function. People call it homogeneous. I've learned it homogeneous, so I'll use that. So if you have a differential equation, in that differential form, where you have the dx and the dy, and these functions m and n, those very same functions that we were just looking at, are homogeneous functions. That means you drop a t in there, t times x, t times y, and then you're able to factor out a t so that it'll look like the original function. Then you have a homogeneous differential equation. And if you do have a homogeneous differential equation, the substitution that you'll make is that you're going to introduce a new variable, and the new variable is either u or v. But you'll introduce a new variable, and you'll replace either x or y, depending on how you do your substitution. Now, in most of these cases, either substitution would work, but in some cases, one of them will work and one will not, or one of them would be more difficult than the other. And I don't have a key on which one to use, so good luck. Basically, if you do a substitution and 2 hours have passed and you're still doing the same problem, maybe you try the other substitution. Okay, let's take a look at a problem. I think for this section, I actually picked out problems from the book. Let's take a look at these problems and see if we can try them out. So this is section 2.5 or 2.4? 2.5. I think, yeah, 2.4 was exact. So 2.5 is substitution section. And this is from the back of the book, or the back of the section. So we have m and n, and now we want to identify if they're exact differential equations. So not exact, sorry, if they are homogeneous. So let's check. We should check if they're exact first, right? Because if they're exact, then we know how to do this. It's not. So let's move on. So let's check if it's homogeneous. And the way to check that is that if you take m, and then in place of x, you would put tx, and in place of y, you put ty. You can pull out a t squared, I think. So this is ty quantity squared plus ty times tx. And they both have a t squared associated with it. And then after you've pulled out the t's, you look at this and say, oh, that's just exactly like your m of xy function. Right? So you can say, yes, this is homogeneous. Should I put a yx here? So I know m is homogeneous. Let's check n. N, and this time we're going to put tx in for x and ty in for y. Well, this is negative x squared, and there's no y, so I'll put a tx in for x. That becomes negative t squared x squared. That's just a t squared times negative x squared. And negative x squared was your original n function. So yes, this is also homogeneous. It has to work for both for you to be able to do this. Yeah? Yeah, it should be the same same order. I think they called it a degree. It's the same degree. Okay? So this would be a good candidate for substitution. Let's see. Let's substitute y is equal to u times x, where u is another variable. We're going to pretend that that's a variable. Now, just like in our u substitution with integrals, we have to also take care of the differentials. Differentials exist here. So let's take the derivative of this thing using differentials. So dy, the differential. Now these two are supposedly functions, so I need to treat them like they're functions, which means I have to use a product rule. So derivative of the first times the second plus the first times the derivative of the second. Okay? So what I've essentially done is I found a substitution not just for the y's, but also for the dy. Okay? Because when you do your substitutions, you have to also take care of the differentials as well. Now, how is this going to look like? Let's see. Y is equal to u times x, so ux squared plus ux times x. Dx minus, probably need a little bit more room here. Minus x squared times, now the dy needs to be replaced, and the dy is a little bit more complicated, right? So this, I'm going to just switch to order x du plus u dx equals 0. Okay, let's try to simplify and do some algebra at the same time. Should we call this u squared x squared? Maybe, I don't know. U squared x squared. I'm going to need to deal with this dx, so I'm going to separate this all into different terms, and then we'll regroup later on. Plus u x squared. Oh, they both have a dx, so I meant to put a dx on both of them. Dx. Dx minus, this is going to be x cubed du minus x squared u dx equals 0. Is good so far? Man, tedious algebra. I hope I don't make any mistakes here. Like leave out a negative sign. So one thing I did notice is that there's a u times x squared dx, one with a positive sign and one with a negative sign. So that goes away. And then we have u squared x squared dx minus x cubed du is equal to 0. I can probably factor out an x squared if I want, right? And divide it out since it's 0 on the other side anyways. So let's get rid of an x squared. So this is u squared dx minus x du is equal to 0. That looks a lot simpler, but how would we solve for this? Separable. Let's put the du on one side. So that'll make this positive. And then du over u squared is equal to dx over x. Right? So bring it over, separate the u's and the x's. So now let's integrate. Now that it's a separable differential equation, maybe we should put separable. Separable. So let's integrate. What's the antiderivative of this? U negative 1 over negative 1. And the antiderivative of the 1 over x? ln x. Okay, so let's throw the plus c in there because it's still arbitrary. Is this our answer? No, because we started with an x and a y, and now we have a u. Remember the u substitution that you guys did in integrals? After you found the u's, you have to change it back into x's. So after I found my u, what does u equal to? Y over x. So the reciprocal, I guess, x over y. And I think we can continue solving for y here to get an explicit solution. So we need to take the reciprocal and multiply by x, right? To get y by itself. So y is equal to take the reciprocal and then multiply by x that was in the denominator. Let's just multiply by negative x. And here's your solution. An explicit solution with an arbitrary constant. Okay. Questions? That was kind of fun. Yeah.
I would say that for the substitution, x equals to u times 1.
Yeah. And I don't know if it's going to be easier or more difficult, or maybe it'll be exactly the same way. But yeah, if you do it that way and follow along, then it should work out to be the same. I think for something like this, these are polynomials, so it's fairly simple, and I think it'll turn out okay. If you start having exponential functions involved with the exponential function, that might be a little bit more tricky. Just remember this, though. Don't forget about this this part of the substitution. Oh, because I want everything in terms of x's and y's, and if it's already an x, then it's already an x. So the only thing I want to get rid of are the variables that are introduced. In this case, the u was introduced, so I want to get rid of that. If you did the other substitution, you would introduce v. I think you would have introduced a new variable v, and you would need to get rid of all the new variables you introduced because you want to start with whatever you started with.
The u is a constant number.
No, it's a variable. It's a variable. So you have to treat u as a variable, and we saw that in this differentiation when we had to find the differential. So u is a variable, not a constant. Any other questions? All right. So this is one type of substitution. Let's take a look at another type of substitution that would help us solve for some differential equations. A Bernoulli equation. So a differential equation of this form, it almost looks like a first order linear differential equation, except the right-hand side has a y to some power in it. Okay, this little bit over here this little thing makes it non-linear. If it was a linear differential equation, we'll use that, integrating factor business and solve. But here we have a y to the n at the end, and that we can't do anything about that. So that's not linear. And so but if it looks almost linear except for that little bit over there, this is called a Bernoulli equation. All right. So the substitution for a Bernoulli equation would be another introduction of a u variable. U is equal to y to the 1 minus n. That's a weird substitution, but it'll work, so let's just trust it. So let's do an example. Should we do what's that called? IVP? Let's do initial value problem. 21 or 22? 22. So we have an initial value problem, which means we have a differential equation with an initial condition. Now, at this point, when you first look at this, you say, I'm not sure if this is a Bernoulli equation yet. Let's see. Let's figure it out. And so to do so, you need to put it in standard form, get the dy dx by itself. So I will divide out by y to the 1/2. So dy dx y to the 1/2. So 3/2 minus 1/2. That's just 1, right? And then this is y to the 1/2 in the denominator. So I'm just going to write y to the negative 1/2. Well, it looks like a Bernoulli equation. We have our p of x is equal to 1, if we want to look at it that way. Our f of x is also equal to 1. But that's not the important part, right? The important part is that n is equal to negative 1/2. Okay? So if that's your n, your substitution will be u. U is equal to y to the 1 minus n, negative 1/2. So that's y to the 3/2, right? Okay? Now, this particular substitution doesn't have a dx dy business, but we can think about splitting it up like that. But we can assume that u is a function of x. So we can replace this du dx is equal to the derivative. What's the derivative of y to the 3/2? 3/2 y to the 1/2 times dy. Oh, maybe I should have done this a slightly different way. Let's hold off on this for a minute. Let me take a look at this function again, or this relationship. U is equal to y to the 3/2. What's y equal to in this case? U to the 2/3? Is that right? I got to think about this for a minute. I think it's right. Yeah, okay, square root of both sides and cube root. Okay, so that's right. So now let me take it from here instead of taking the derivative of u here. Let's take it from here because we want to replace the y's with the u's, and then we also want to replace the dy dx with a u. So this is 2/3 u to the -1/3, right? And then there's a du dx as part of the chain rule. So this is what we will replace the dy dx with. So let's cross out the other substitute or the other differential that we did, just so we don't worry about that part. And let's remember that we want to get y by itself because we're going to replace y in our differential equation. So we're going to get y by itself before we do the differential. Okay, now let's replace everything and see how it goes. Hopefully this will turn out nicely. It better, right? 2/3 u to the -1/3 times du dx minus y is equal to u to the -1/3 is equal to, I'm going to do it like this first, u to the -1/3 raised to the -1/2. Oh, yeah. Thank you. 2/3, right? 2/3. Is that cool now? Y. So it should be plus. Wow, good job. Those darn negative signs. Okay, now the whole point in this substitution is, do you know the point is to this substitution? The whole point of this substitution is to actually make it look like a first-order linear differential equation. The original problem was not a first-order linear differential equation, but hopefully this will be after we simplify it out. So we will, let me first simplify the right-hand side. This looks like it's going to be u to the negative 1/3. I just multiply the powers, right? All right, now I'm going to divide by 2/3 u to the negative 1/3 so that I will have my differential equation in standard form where I just have the derivative by itself. And if I do that, I'm going to get a constant 3/2, and I have u to the 2/3 divided by u to the negative 1/3. That's like multiplying u to the 2/3 times 1/3. You add the powers, you get u to the first power. And this will cancel this out and would also leave me with a constant 3/2. Okay? Now you're pretty much done here. Well, except for, the other stuff. So, what's the other stuff? Now it's a first order linear differential equation, so we can use the integrating factors. So let's let u, or mu, let's exaggerate this mu so that we know it's different from the u substitution that we just did, is equal to e to the integral of p of x. It's just a constant, 3/2 dx. So this is just going to equal to e to the 3/2 x. Is that right? Yeah? Okay. Can I get 2 nods? Just one guy nodding. Anybody? Is this right? Yeah, okay. So I know that this is my integrating factor, so I know that my left-hand side is going to be the integrating factor times u, and then the right-hand side I would need to integrate the 3/2 times the integrating factor. Are you guys comfortable with this step? I skipped like 3 steps, 2 or 3 steps. So I multiplied this differential equation by the integrating factor, and then I noticed that the left-hand side was a product rule. So I packaged it together as a product rule, and then so this also got multiplied by the integrating factor. And then I integrated both sides, so I undid the product rule, and so I just have the product on the left side. And now I have the integral of the right side with the integrating factor. All right, this is easy enough. Antiderivative of e to the 3/2 x is e to the 3/2 x divided by 3/2. That would cancel the 3/2 over here. And then I throw in a plus c. So I get u is equal to, it looks like the 3/2 would cancel here, right? The e to the 3/2 x would cancel. So that's just a 1 plus c over e to the 3/2 x. And then instead of putting a fraction down, I'm just going to write the negative exponent to say that it's in the denominator. Okay, we done? Oh, what do we have to? Got to change it back, right? Let's see, u is equal to y to the 3/2. So that's minor steps here. Y to the 3/2 equals 1 plus c e to the negative 3/2 x. And then just undo this. By taking both sides to the 2/3 power and now you have an explicit solution. Now am I done? Yeah, except for the initial condition. You guys can figure out the initial condition. 0 in for x, 4 in for y, solve for c, and then you're really done. Okay? How's it going? Is this heavy stuff, or is this kind of light and fun? There's no response, so I would... What? Heavy and fun. Good answer. Okay, let's do one more substitution. The other one really falls into a very, very, very special case where you can group a lot of these things together. So our last type of substitution for today is a differential equation that has a special form where you see a linear combination of x and y and then the constant, so ax plus by plus c, where a or b or c can be 0, and so you might just have one variable. Or except no, b can't be 0 because we need the y in there. And if a and b were equal to 0, this would be, or a and c were equal to 0, then this is just a what do you call it? What's that called? When you just have dy dx is something with just a y in it, there's no x's? Autonomous? Remember that? Autonomous differential equation, then you have the, what's that vertical line thing called? Where you have arrows? Phase portrait? Yeah. And then if they approach a point, what's that called? Sync? And then if they go away from the point, it's called a unstable. Yeah. Remember that? So your worksheet is due tomorrow, I guess. It's supposed to be due tonight, right? Somebody just asked to postpone, so I'll postpone it till tomorrow. But that's where all this stuff was, autonomous differential equations. Anyways, let's see if we could do one of these problems. Which one should we do? I don't know. They're all easy. Maybe not. 23, I would assume, would be the easiest. Let's do that one. So because this whole polynomial is being squared, it makes this a non-linear anymore. That makes it quite difficult, and we can't separate it. So those are your first two choices. You either separate it or you put it in a linear, first-order linear differential equation form. If you can't do that, you have to check, can this be exact or separate it? Or now we're out of options except for possible U substitution. So our substitution is that taking this polynomial of x and y and then writing it as u. And then what we'll do is we'll approach this with a dy dx differential. So we'll assume that u is going to be a function of x and y is a function of x, and then x is just x. So basically what I'm saying here is let's take the derivative of this with respect to x. So the derivative of u with respect to x is equal to the derivative of x with respect to x. That's just 1. The derivative of y with respect to x, dy dx, and the derivative of a constant with respect to x disappears. So here's our substitution. We'll take this information and plug it into here. So the dy dx is du dx minus 1. We'll bring the 1 over to the other side. Du dx minus 1 is equal to, now on the other side is this thing, u squared. So there's a constant 1 out there. Let's add it to both sides. Du dx is equal to u squared plus 1. That doesn't look like it's linear. Oh, for thought process. Which one should go first? What do we want to try to do? When you're faced with a differential equation, what's the first thing you look for? Separate. Can we separate this? Oh, I think we can. Right? Hey, this looks like an autonomous differential equation. So let's separate it and integrate. I want the integrals in red. You guys remember what the integral on the left-hand side is? Arctan. So integral of 1 with respect to x is just x, and now is the time for a constant. We'll put the constant over there. We want to solve for y. We need y back. So let's get y back. Arctan of x plus y plus 1 is equal to x plus c. And again, if there's any chance of solving for the y, go for it. Is there a chance solving for a y? Let's take the tangent of both sides, shall we? X plus y plus 1 is equal to the tangent of x plus c. And then now just have a couple of an x and a y laying around there. Let's just throw that on the other side. Tangent of x plus c minus x minus 1. Now we have an explicit solution. Okay. So there's a lot of computational stuff, or a lot of formula computation and stuff that should remind you of things kind of like things we did in Calc 2. You want to transform an integral into something that you can integrate. It's the same idea here. If you do it arbitrarily, like if you follow some of the proofs in the book, you'll see why when you do a certain substitution, it becomes, in this case, separable differential equation. Or in the case of Bernoulli, when you do the substitution, you change this nonlinear, first-order nonlinear into a first-order linear differential equation. And then for the first substitution that we did when we had homogeneous differential equations, these things turned out to be separable also. So these substitutions make these differential equations look like either a separable differential equation or a first-order linear differential equation, which we should be able to handle now. And make sure you get cracking on your homework. It's due tonight, so that you can get the practice on these types of differential equations, so that when it comes time to do this homework, you're comfortable enough to follow through a first-order or separable DE. All right? So there's a quiz on Tuesday. The quiz is going to be on the first-order differential equations, since we're supposed to have it today, but we didn't get to it. So, all right. And if there's any issues that you guys have, you send me an email, and then I'll try to answer it, or if I check my email. And if there's something that really is something glaring in the homework or something like that, I'll do a little video of it so you can see the solutions. All right. Question? No, the quiz won't be on this stuff. The quiz will be on the first order differential, which is 2.3, something like that. All right. Have a good weekend. Oh, yeah, holiday on Monday, but I don't see you on Monday anyways.